Hello, students. Welcome back. So, in this session, we are going to learn what is skewness, what are some of the examples of skewness, how do we even measure skewness, and why do we care about skewness? A data that has symmetrical distribution, its mean, median, and mode, they will always be same. Another name for symmetrical distribution is normal distribution. The shape of your normal distribution, it generally resembles a bell-shaped curve like this right here. Now, sometimes the data is not symmetrical, as shown in this image and as shown in this image. The curve can be skewed. For example, like right here, it is skewed towards the right direction right here. In this case, it is skewed towards the left. Now, a skewness, it measures how much your data is far from being symmetrical. That's what your skewness does. A skewness of 0, it indicates a symmetrical distribution like this right here. Here, my mean, median, mode are same. On the other hand, a positive skewness, another name for that is right skew. It indicates that my tail for this distribution is extending more towards the right hand side. In other words, you have more data points clustered on the left hand side, which is this part right here. Your positive skewness also indicates the presence of outliers towards this direction right here. Because of the outlier, my tail is extending towards the right. On the other hand, negative skewness, another name for that is left skew. This indicates that the tail is extending further towards the left. This is like opposite of the top one right here. Now this indicates that my more data points, they are clustered towards the right hand side of my curve, which is this area right here. This also indicates, just like the top one, that your outliers, they are present towards the left side of your curve, which is on this side. That's why your curve is extending in this direction. Here, my mean is going to be smaller than median, is going to be smaller than mode. Now, let's look at some of the examples of skewness. Let's start with zero skewedness. A very good example of zero skewedness would be the height distribution. Most of the people, their height is symmetrical about the mean. If let's say the mean height of some individuals in a country is 1.77 meter, then you are going to notice that the height distribution would be symmetrical about 1.77 meter. Your mean, median, and mode is going to be this value right here. Now, let's look at examples of right skewedness. Income distribution. A large portion of the population, they earn a moderate amount of salary, a moderate amount of income. But there are few individuals, few people, they earn extremely high income. Their salary is very high. They fall in this area right here. And because of the presence of these people, your distribution becomes more skewed towards the right. So your curve extends towards the right. Another example would be test scores. In education, most students, they score around the average. So this is around your average. This is where most of your students they score. But there are few exceptional students whose score is very high. And because of them, because of these high scoring students, your distribution curve, it will become right skewed like this. Now let's look at some examples of left skewedness, death from natural cause. Most of the death that happens from the natural cause, they happen at older age, right here in the older age. But occasionally you may come across some cases where people die at a very young age because of natural cause. And these are those people, young people. And because of them, this curve, it gets skewed towards the left. Another example would be score on an easy test right here. Uh, if student, let's say, take a test and the test is very easy, then most of my students, they are going to be scoring in this region right here. high score. They're going to have a high score. But there are few students who may not end up scoring high. They may end up scoring low. They will fall in this region. And because of that, your distribution curve would be skewed towards the left. So, how do we even measure skewness? Well, there are many formulas, but the most common approach is the Pearson's moment coefficient of skewness. This is the most common one, and this is the formula for that. Same thing can be rewritten in this way. They both are essentially same. Over here, I'm just using my data points, my x1, x2, x3, all the way up to xn. These are my data points. My x bar, which is this right here, this is my mean value. This is my actually sample mean. All right. And right here, that is the number of points I have. Uh, on the other hand, if let's say if the sample standard deviation is given to you, the S is given to you, then you can use this formula right here. Now, when we get this number, the skewness number, how do we read that? Well, if your answer is between minus 0.5 to plus 0.5, then for the most part, you can consider your curve as symmetrical. So your curve, you can go something like that. On the other hand, if your value falls in this region from minus 0.5 to minus 1, or if it falls from plus 0.5 to plus 1, then your curve is said to be moderately skewed. So your curve maybe look like something like this in this direction, or it could be look something like this, like that. On the other hand, if your value is from plus 1 to higher value or minus 1 to lower value, then your curve, then your skewness is actually your distribution curve is very highly skewed. Your curve may look something like that, like that. In this case, it may look something like that. So why does skewness matter? Number one, skewness, they help detect non-normality. Now, many algorithms like your linear regression, logistic regression, your PCA, which is short for principal component analysis, they assume that your data or your residuals, they are normally distributed. But if your data is highly skewed, then this assumption is no longer true. That would lead to your model, to your machine learning model, it would be biased. And therefore, it would not be making a reliable prediction. It will result in a poor predictions. So skewness also impact your feature scaling. If you recall, in feature scaling, we used standard scalar or z-score. Now, if you have skewed feature, that would distort your mean and standard deviation. So the solution in this case is to apply log, square root, or Box-Cox transformation to reduce your skewness. Now, they can also help improve your model performance. So there are some AI and machine learning models like tree-based one. For example, your decision tree, your random forest, your XGBoost, they tend to be less sensitive towards your skewness. But there are some linear or distance-based model. For example, your KNN, which is K nearest neighbor, your support vector machine, they can perform better after your skewness correction.